something that Sundar asked last time on sphericality. So suppose that P is a connected planar algebra. And so then P is spherical. So if and only if the left trace and right trace on P1 are the same. So this is the statement. Let's just try to justify this at least a little bit. So proof, of course this is by definition special case. So all tangles which are equivalent on the surface of a sphere should give the same answer, and these two are certainly equivalent on the surface of a sphere, so they will give the same answer. So sphericality implies this. And what about this? So for this we will use something we have said several times before. So these things are both, you can consider them as elements of, say, since I didn't indicate the outside shading, let me just say just for P1 plus is sufficient. Okay. So yeah. So to do this side, so if T and T twiddle are zero tangles, I won't say plus or minus, just say zero tangles, equivalent on the surface of a sphere, this we have used several times before, then we may move string by string across the point at infinity. To obtain T twiddle from T. So to verify that sphericality holds, it suffices to do it for just moving one string across the point at infinity. Which one?
What if there are no strings?
If there are no strings, then there is T and T tilde are already equivalent on the plane itself. The whole thing of sphericality is taking a string across. If there is no string, then it's trivially true. So I want to move string by string. So here is the some connection. So T is something like this. It's a zero tangle, and here is the point at infinity, say, and there is some string which you move. So let's say there's a string like this, and these are connected in some ways. I don't care. So if I move this across the point at infinity, then so if I call this one T, then T twiddle will be something like this. So here I don't care about the connections, and this string has now come this way. The same string, after moving across that point at infinity, I have gone across and come around, and now that has turned into this. Now we want to verify that these two give the same answer. So what we do is, you enclose the rest of it in a one box. So essentially this will follow then. So T and T twiddle will have equal value if we assume this condition. on just P1 plus. So why just P1 plus? It could be shaded, this box we could shade it in two ways. I want to say that, how do I say? I want to say that this thing is, corresponds to one of this, and this one corresponds to one, by interchanging the roles of, if there is a 1 minus. I am not saying it clearly. Okay, so there are two possibilities. So suppose this region is shaded black, right? And so now this region is shaded black, so the outside is shaded white. But now you move this black across, so this will be shaded black, right? That means the entire the entire outside will be shaded black. So this is wrong, right? So this entire thing will be black. So this is a 0 plus initially. Now here is a 0 minus. And we want to see that these two values are the same. So on this side, here we have, this is a, if I shade it, if I put these boxes here, and if this thing belongs to P1 plus, this is shaded white, so this is shaded black, and when it comes back here, this is shaded black. So we have this. So I want to say that by applying, by putting this element in a box, so I have this box in a one box, and I have this shaded like this, and that matches exactly with this picture. This will match exactly with the other picture. So if it is shaded like this, there is no problem. What if it is shaded the other way? So then how do I use this? So let's just see that. So T is, let me do the same thing, except now it is, so this is the point at infinity. And suppose this is shaded white, so the outside is shaded black. And then T twiddle is this, and these two are joined this way, and here this is shaded, this box is here, this part is shaded black, and the outside is shaded white. So I want to apply this same thing, but I'll apply it to T twiddle. I'll look at it the other way, take it around, look at it inverted, so then this will match this picture and that will match this picture. So whichever way I do it, just on P1 plus, I don't need to include the one for P1 minus, that's all I'm trying to say. Okay, so essentially that proves this sphericality criteria, and therefore what I did with a lot of difficulty last time, it's trivial. Hence for PV, sphericality holds. And that's because we showed that for the algebra PV, P1 plus is just isomorphic to end V. So end V to PV is an isomorphism. This map is given by P goes to this element. This we showed was an isomorphism. End V to PV 1 plus, yeah. 1 plus, yeah. This is an isomorphism. We showed this. And so to verify sphericality, all you need to show is that for an element of this kind, if I close it this way or I close it that way, I get the same answer. But that's what I put into the relations itself, the trace relation on PV says exactly the hypothesis of that proposition. If I take T and close it this way, it's trace T equals T closed the other way. And so by this thing, sphericality holds. Okay. So that's so much about sphericality. So to verify that PV is a planar algebra, a subfactor planar algebra, the last and most important step is to show that the trace is positive, faithful positive trace. The normalized trace on every pk is a faithful positive trace. Okay, so to do that, here's what we do. So just like we had this isomorphism from end V to PV1 plus, we have an isomorphism from a tensor product of end V's and end V ops to PVK plus. So we have an isomorphism from PV end V tensor end V op, the alternating k copies to PV k plus. And we also have for k minus, where it begins with end V op and then alternates. So we have an isomorphism of this kind given by T1, T2 op, T3 goes to T1, T2, this we showed was an isomorphism from this space to that space. In particular, this has dimension n to the power 2k. Okay, so we have this isomorphism. I want to look at this isomorphism more closely. So we want to say that the trace is positive. So let us see what this does to the star. So what does this isomorphism do to the star? So this isomorphism is a star isomorphism. Okay, so why is that? So what is the star on this side? So the star on this side, so it's a tensor product of algebras. Each one is a star algebra, and the star is just the star of each one separately. So T1 tensor T2 op tensor T3 star is T1 star tensor. Now you have T2 op star, but T2 op star, the opposite has the same star as the original. That means it's T2 star op tensor T3. So it's a star algebra with this structure. And on the other hand here, what is the star of that? So the star, so this tangle is this. If I write the external box, it looks like this. And if I star this, since it's a star planar algebra, I have to star that tangle and put in all the stars of these elements. So this by definition is, so I reflect it, and so this doesn't change at all, but I have to put in the stars there. Since PV is a star planar algebra. And that's where this goes to. By definition of this map, this element goes there. So you have a star isomorphism from this algebra to that algebra. And further, this isomorphism preserves the traces on both sides, the normalized traces on both sides. This star isomorphism preserves the normalized traces on both sides. So how is that? So what is the trace on this tensor product of algebras? So trace of T1 tensor T2 op is the normalized trace of T1 times the normalized trace of T2 dot dot dot. That is the trace on this tensor product of algebras. That's on this side. And on the other side, what is the trace? While on the PV side, the picture trace is this one. So T1, T2, so on, and you close it all up. So there's the now that gives you an element in this case of P0 plus, and what element is it? We use the relations, so we know that when you have a single thing and close it, it's just the trace of T3. So this is finally gives you the product of trace T1, trace T2, trace T3, so on. And so the normalized trace, if you take, it is n to the power minus k times this, that is one n will go away from here, one n from here, and one n from here. So the normalized trace is the normalized trace of T1 times the normalized trace of T2, so on. Okay, so it's a trace preserving star algebra isomorphism, and on this side, this is just a matrix algebra. This is just a tensor product of matrix algebras. So this side is a matrix algebra, and it has only one trace, one normalized trace, and that we know is faithful and positive, and so it goes over to that trace there. Therefore, the other side also, the trace is faithful and positive. So since LHS has faithful positive trace, by a star isomorphism transporting by that preserves trace, RHS also has faithful positive trace. And so that finally completes the proof that PV is a subfactor planar algebra. So we have proved the following. So in Jones' paper on planar algebras, PV is introduced in a different way. So I want to spend some time on that, and I don't have all the proofs for that one, but we'll see some things are missing. I'll try to tie it up to this PV. Okay. So another version of the planar algebra of an inner product space. So let's call this one Q of V. So define a planar algebra Q by the following. So how does one define a planar algebra? We have been doing it by generators and relations. So we want to specify the vector spaces and we want to specify all the maps. So what are the vector spaces for this one and what are the maps? So set Qk plus equals V tensor V star tensor power k, and qk minus equals v star tensor v tensor power k. So in particular, q0 plus minus are both the empty tensor product, which means just the complex numbers. So this defines the vector spaces, and then there is a tangle action defined by the following rule. Now the rule, it's a bit hard to state in general, so let me introduce that rule with an example.
Your earlier example, P3, will have only three terms, V star V.
End V, end V, end V, end V op, end V.
Oh.
Now it is V star. So it's the same spaces. Okay, so example of how to define ZT. From this example you can see what the general rule is. It's a little hard to say explicitly. So here is my tangle T. Here is a tangle with three internal discs D1, D2, D3, and the stars as follows. Let's say like this, shading like this. And inside this will be so let's take that tangle. And for this we want to define ZT. So where should ZT go from? So here ZT goes from, so in this case this is a P1 minus. This one is a P2 plus. And this third one is also a P1 minus. And the final one, I didn't put the star, so let's say the star is this one, this arc. So it's going into P2 minus. So I have to specify such a map ZT. Given this picture, I have to tell you, okay, it's all Q's, right? I call this planar algebra Q. So Q1 minus, Q2 plus, Q1 minus, Q2 minus. So I have to specify a map where the Qk plus and minus are given by these formulas. So the way this map is going to be specified is follows. So what is Q1 minus? Q1 minus is V star tensor V. Q2 plus is VV star, VV star. Another Q1 minus is V star V. And the final is V star V, V star V. So I have to specify such a map. Now this map is going to be specified by saying how a typical element of the dual space of this acts on the result. So the map is specified by giving a scalar for each element of the dual space of the target. In this case, the target is Q2 minus. So for each element of Q2 minus star, I'll give you a number, and that's going to, it will be a linear function. That's a linear functional acting on that vector. I'm going to specify completely that vector. So how do I do that? And what goes inside these? So inside these, we must take elements of these. I'll specify it only on the decomposable tensors, and on the others extend by linearity. So for example, for this one, the space associated to this one is V star tensor V. So I'll take a F and a V here. I'll put in an F and a V. I start at the star arc and then start from there. The points I'll label by F, V. Here, so it's an element of V, V star, V, V star. So let's take G and a W. So let's say here it is W1, G1, W2, G2. And here again it's an F and a V. So I'll call that a K and a C in this case. So in this case K and C. And finally for the outside, I have to take an element of this dual space. So of this dual space, so I'll call that something. So the dual space of Q2 minus is V, V star, V, V star. And take an element there. Take a decomposable element there. Say U1, P1, U2, P2. And then you label this thing with U1, P1, U2, P2. Starting from the star arc, U1, P1, U2, P2. Now, associated to all of this, I'll produce a number. So from here, we get the following scalar. And what is that scalar? If you look at this picture, it has various strings. All these strings, at least all the open strings, which this is a closed string here, never mind the closed string. All the open strings have these endpoints, and the endpoints are always, one of them is labeled with an element of V, one of them is labeled with an element of V star. So you take the scalar, you just evaluate these scalars. So for this string, you have P2 acting on W1. P2, W1. For this string, you have G1, W2. For this string, you have G2 of C. For this string, you have K of U2. For this string, you have P1 of U1. And for this one, you have F of V. And then for the open strings, for every closed string, you put in an n power, you just put in one n into n power number of closed strings. 1 equals here number of closed strings into n power 1. So this is a number that is associated to this picture decorated with all this data. And this number specifies the action of a dual basis of this on the result, and therefore it specifies the result completely. So this is the definition of ZT. This definition of ZT is done in this way. With this definition, how do we know it's a planar algebra with this definition? So let me just say two things are clear and one thing is not too clear. So with this definition, So the renumbering axiom and the non-degeneracy axiom are easy to see. The way the thing is defined, it is easy to see that it's independent of the numbering, and non-degeneracy can explicitly be checked for that tangle. By following this procedure, you can verify that the identity tangle gives the identity map. Those two are easy. But the substitution axiom is somewhat difficult. At this point, I don't really have any proof that I am completely satisfied with to show that the substitution axiom holds for this one. But I am going to assume it. So we'll assume that this holds. If you assume that this holds, then we have a planar algebra. We have a planar algebra Q of V. So then we will have a planar algebra Q of V. And we don't want just a planar algebra, we want a star structure on this. So I have to tell you how you take the star of something. So PV, let's say K plus, is V tensor V star, tensor V star, so on. So how do you take a star of a typical element here? So to define star, define as follows. So you take on decomposable tensors as usual. So V1 F1, V2 F2, Vk Fk. If I take the star of this, I'll just say this way, equals inner product with Fk tensor inner product with Vk tensor inner product Fk minus 1 tensor inner product Vk minus 1 up to inner product F1 inner product V1. So what exactly does this mean? So let me just clarify the meaning of these symbols here. So V is an element here, inner product with V is an element of V star. So for V in V, inner product with V is an element of V star, and this mapping is an isomorphism, conjugate linear isomorphism between V and V star. And the notation I have chosen is such that the inverse will be denoted F goes to inner product with F. That is, if F is inner product with V, then V is inner product with F. That's how I've chosen the notation. So the star is a conjugate linear map defined as follows. So this makes P of V into a star planar algebra. Q into a star planar algebra. And what I want to show is that the planar algebra that we have defined, P of V, is isomorphic to Q of V as star planar algebras. That is, if you assume that Q of V is, since I haven't been able to prove carefully that Q is a planar algebra, you assume that Q is a planar algebra, but then we can show that P and Q are the same. So in fact, whenever you are dealing with Q, you may as well be dealing with P, which we know properly, carefully we have done that, P of V is a subfactor planar algebra. So how do you prove this one? Prove, and that's another advantage of the way we are doing P of V. We are doing P of V by generators and relations. So if you want to show that it's isomorphic, then you just map the generators arbitrarily to some nice things and then show that the relations hold. That will show that there is a map of planar algebras from one side to the other. You still have to show that it is 1 to 1 and on to. So, and these are very natural maps that do this. So define the map PV to QV by first defining P of L to QV, where L is the label set and V. So that's the first step. So how do you do this? Defining a map from the universal planar algebra of a set to any other planar algebra just means I have to give you a map, set map from this L into that planar algebra QV, which preserves color. So to do this, consider the map from L into QV1 plus, defined as follows. So I have to give you a map from the label set L1 plus, L is the same as L1 plus, to QV1 plus. I have to tell you what the map is. So what is this side? This is L is identified with end V, and this side is V tensor V star. So I want a map here from end V to V tensor V star. It's a natural map. For example, it's easiest to specify it by its inverse. The map V tensor F goes to TVF, where TVF of W is F of W times V. So this is the natural isomorphism between end V and V tensor V star. This way, I want the inverse map. The inverse map, you want to specify it, you will have to use some kind of a basis, and although the map is independent of basis, some kind of basis one needs to use in order to specify the map going this way. But whatever it is, we have a natural isomorphism from end V to V tensor V star, and hence from L into QV1 plus. And once you have a map from a label set into a planar algebra, you have an extension map from the planar algebra PL of the set into that same planar algebra QV. Now what one needs to do is, we need to check that all the relations are satisfied. So to show that this map descends to PV, we need to check that all the relations hold. All the relations for PV hold. And we had 5 of them: linearity, unit, multiplication, trace, and Jones projection. So let me do some and I'll leave some. So let me leave linearity. That is easy. That just follows from the fact that this map is a linear map. This map, initially, all you need to define the map from PL into here is a set map from here to there, but this map is not just a set map, this map is a linear map, and from that the linearity holds. So forget linearity. Let's see the unit relation. So the unit relation says that if you have id V here, this is equal to this. So if you put it in a box, then that reads this way. So we want to check this relation. So what we want to do is we want to send these elements to the corresponding elements inside that planar algebra and see what happens under this map. So the map id_v, where does id_v go? So id_v goes to an element of V tensor V star, and what is that element of V tensor V star? So ing_v to V tensor V star. Where does this map id_v go? So as I said, if you want to specify the map this way, you will have to use some kind of a basis. So it goes to sigma over a indexing set for a basis ei tensor ei, where ei is a basis for V with dual basis E upper I. One can check that this is correct by just operating on any element x. Ei of x, ei is just the expansion of x in terms of this ei basis. So it just gives back x. Okay. So what do we need to see therefore? In QV we need to check. So I'm not saying this right. Ei tensor ei is yeah. Right. So in Q of V we need to check that ei tensor ei equals this element of Q of V. Okay, that's what we need to check in QV1 plus. So how does this give you an element of QV1 plus? So by the procedure, described, if we take this, how is this supposed to give you an element of, in this case, V tensor V star? If I take an element of V star tensor V, and then so this associates to this the number f of V, because there's only a single string and f and v are joined, so this associates f of v. So this corresponds to the element that when evaluated, thus this corresponds to that element of V tensor V star evaluating f tensor V on which gives f of V. But then one checks that if you evaluate f tensor V on this side, but then f tensor V evaluated on sigma ei tensor ei over I f of ei eiv, but this is summation over I ei of v and this is f of v. This is just the expansion of v. So these two are the same. So by definition of this tangle action, this element of that planar algebra Q of v actually represents sigma of over I ei tensor ei. So this shows the unit axiom. Then we have multiplication. Okay, so multiplication. So for multiplication, we need to check that if we have S and T, this is ST. So again we push this down to Q. So pushing to QV, what does this give? Okay, so where does S go? So S goes to sigma SEI tensor EI, and T goes to sigma TEJ tensor EJ INJ. So what we want to do is we want to multiply these two elements together in Q of V. So let's see. So SEI EI multiplied with TEJ EJ. In Q of V, you want to multiply these two and want to calculate the result. So to calculate the result, we take an element again as there, we take an F tensor V and operate it and see what the result is. So this number is summation over INJ F SEI and EI of TEJ and EJ of V. So this is sum over, notice that this is EI of TEJ EI is F of S of TEJ EJV. This is summed over J, and EJ EJV just gives V. So this gives F ST of V. On the other hand, if you take ST, so this goes to STEI, let's say EK, tensor EK under this map, and this, if you evaluate F tensor V on this of this element, also gives F of ST of V. So both of these correspond to the same thing. So this proves that the multiplication axiom holds. And what else is there? Trace Jones projection. So the so Jones projection is the only really interesting one. I'll leave that as an exercise. It's done exactly the same way as multiplication. So let me just say as an exercise, check whether the Jones projection relation holds. So once we have done that, so we have two views of this planar algebra associated to a vector space. One is in terms of these, where the tangle action is quite easy to calculate, and the other is in terms of generators and relations, where it's very easy to check whether this planar algebra embeds into some other planar algebra or not by merely checking the various relations. Okay, so with that we complete the planar algebra of a vector space. So the next one that I want to do is something called the spin planar algebra. So in Jones' paper, he calls this a square root of the planar algebra that we just discussed. So the spin planar algebra, this is associated to a positive integer n, and the dimension of let's call this SP k epsilon is equal to n to the k. In contrast to the one that we had just now, we had n to the 2k, and this one has vector space dimensions n to the k. This is not a subfactor planar algebra. In fact, not even connected. But it's very closely related to this planar algebra of a vector space. However, I'm hoping to be able to see all this. However, if you take this spin planar algebra and take its 2 cabling, I'll explain what that is. This is isomorphic to the planar algebra of V, where dim V is n. So in that sense, it is a square root. It's somehow, when you square it, if you think of doing this operation of 2 cabling as squaring a planar algebra, and when you square the spin, you get this planar algebra of a vector space. Okay, I am not quite ready to. I have written down some relations, but I am really not too sure of being able to prove much. So I'll stop here for today. Sorry, I finished very early. We'll begin with the spin planar algebra next time, and I hope to be able to prove all of these things for the next class.